This is the fourth recording or video on proton NMR spectroscopy, and it's the fourth of six in just characterization methods used for organic chemistry. So to kind of review a little bit, our first video just looked at how the NMR worked in a very general way or basic description of how the black box works. And the next two videos really dealt with structure of spectra, looking at unpacking number and position of peaks, how that relates to number of non-equivalent protons. Integration and splitting was the focus in the third video on NMR spectroscopy, proton NMR spectroscopy. And then the fourth one here is going to take a little bit of a change in direction. We've been looking at mostly structure to spectra, where in other words, where we have the structure in front of us and we have to move to what the spectra would look like theoretically. But in this video we're going to move the other way. So it's really not going to be there's not going to be any new information as far as phenomenon in the data, what we have to consider. It's really just going to be a practical issue. We are going to look at problems wherein we start with just the spectra and try to elucidate a structure. So that's this fourth video on proton NMR spectroscopy. Again, it's the fourth of six. The next one will cover C13 and IR spectroscopy, light involving methods, and the last one we'll look at a technique that does not involve light, mass spectrometry. So let's go ahead and consider, just to start this video, what the problem looks like. Then is what you'll be looking at. It's again a spectra to structure problem, so it's not going to involve, I guess, looking at different bits of information. We're still going to look at splitting, integration, number and position of peaks, but we're going to start with spectra and not structure. So what we had is this NMR spectra, and we were given some other information about the structure along with this spectra that follows here. The NMR is shown, and it has the structure that has this NMR has the formula C5H10O. And we know the group, this compound has a carbonyl group. So let's, I guess, say later on we could have determined that by IR. This is a particular type of bonding within the structure. And I'm going to go ahead and draw that so we could say, hey, I know I have an oxygen and a carbon bonded in a double bond as part of a fragment, but I don't know what else is in the structure. I have to look at the NMR spectra for that. So what I'm proposing with this video is that there are three steps to take when you have spectra, some idea either from mass spectrometry or just information given about the molecular formula, how many C's, how many H's, how many O's you have, and maybe some IR data, what you can do to elucidate a structure. First thing, if they give you the formula or you determine the molecular formula, is that you can determine the degree of unsaturation or degree of hydrogen deficiency. We can do that by taking the number of carbons and knowing that if we had no pi bonds or rings, we would have a 2n plus 2 relationship of hydrogens to n number of carbons. Now, if saturated, we would have 2n plus 2 number of hydrogens to the n number of carbons. I should say n number of carbons. So 5 is n. If we have no pi bonds or rings, then we would have 12 hydrogens, because n times 2 plus 2 would be 12. But we don't. We have 10, and oxygen doesn't change that relationship. If it's saturated, you have no pi bonds or rings, then we have a 2n plus 2 number of hydrogens for the n number of carbons. Well, we don't have that. We have 2 less than that. So we have 10 instead of 12. So it's a difference of 2. if we take that difference and divide it by 2, we have 1 degree of unsaturation. So we can take, if you look at the formula, you can take 2n plus 2 minus actual number of H's and divide that by 2. That's just a very basic, I guess, way of coming to this degree of unsaturation, not considering nitrogens, which maybe in problems we'll talk about later. But it's just a very quick way to say, okay, I've got the number of hydrogens if saturated. I'll subtract from that the actual number that I have from the molecular formula. If there's a difference, of course not just 0, then I'll divide that by 2. That's my degree of unsaturation. So we have, this number was 12. In the calculation it's 10 looking at the actual molecule. 12 minus 10 is 2. 2 minus divided by 2 is 2. Is 1, so we have 1 degree of unsaturation. Well, that was kind of expected that we'd at least have 1, because we know we have a carbonyl group. We have a CO double bond. But what you can say then is I have spent my degree of unsaturation. There can be no more pi bonds or rings within the structure that's growing out on this side and it's growing out on this side. I cannot have any more pi bonds or rings. Now let's look at, so that's the first thing we do, is we look at degree of unsaturation, just the relationship of H's to C's, and O does not change that. Then we consider integration and splitting. So let's do the integration first. Let's look at the integration values, and again, they would not be perfect. In the real data, maybe 2.01, 3.15, but it's close to a 2 to 3. Now, knowing that we have the number of hydrogens in the actual structure, we can say, well, it can't be just 2 protons and 3 protons, because that would only give us 5 total protons. And these integration values, again, represents a ratio of hydrogens under this signal and hydrogens under this signal, a ratio of 2 to 3. But we can't say it's just 5 protons. So what we do is just double both sides. We say, well, what if it was a 4-6 combination of hydrogens? 4 and 6, oh, that totals 10. So now, put it in pen, you can say, I know I have 4 H's under this signal and 6 H's under this signal. You can put it in pen right on your data. From the integration, I know I have this number of protons that represent each signal. 4 H's and 6 H's. And looking at the splitting, it's simple, meaning it's not complex. It's a simple quartet. Looks like a triplet. I'm just going to label that quartet. Looks like a triplet. Looks fairly simple. So I'm going to say all 4 protons, because they're in a nice, simple, clean quartet, have to be equivalent. And all 6 protons here, because it's in a nice, clean triplet signal, have to be equivalent. I couldn't make that deduction if this was a very complex signal or had a lot of, maybe a chance of 2 signals overlapping or whatever, but that's not the case here. So the easiest way to make 6 protons equivalent is to propose that I have 2 CH3 groups that have to be equivalent. Have to be equivalent. And the best way to propose 4 protons to be equivalent is to have 2 CH2 groups or methylene groups that are equivalent. We can kind of treat this in like a palette and say, this is what I have to work with. I've got 2 of these groups, 2 of these groups, and a carbonyl, and I'm looking at my number of carbons, 5, 2, there's 2 more, that's 4, this is 5, I have my 1 oxygen. These are my groups on a palette, so to speak, that I can build the structure from. So how do I make 2 methyl groups equivalent off of this carbonyl? Well, I don't want to put one on one side that's different from another on the other side. I want to make them equivalent on either side. So the easiest thing to propose is just to put those 2 methyl groups and the 2 methylene groups on the sides, or equally on the sides of that carbonyl. These 6 protons would be equivalent, and these 4 protons would be equivalent. So I've just made my pentanone. Check. This meets all the criteria for integration. They are equal, the 6 and the 4. Let's look at splitting. If we put the methyl group next to the methylene, we'd expect for this signal to be, as far as splitting goes, a triplet. Why? Not because there's a 3 here. Remember, splitting, it's all about your neighbors. So if you think you have something going on for these 3 protons and you just want to know they're splitting, you don't grab them. You go and find their neighbor. So let's take, out of these 6, we're going to take a representative, so I'll just grab one of those and take a walk. I take a walk over here, I have 2 protons. 2 protons as neighbors, it's an n+1 rule. I'm expecting a triplet for this signal. So of course we see that, we see a triplet. And so, well, why don't I look at this side? Again, remember you can pick a representative of those 6. So pick either side, pick one. Whatever's true for one is true for all. We can do the same thing over here. I can pick any one of these 4 protons. Kind of hold it and think, or put my pin on it and ask, what's its splitting look like? Where do I go? To my neighbor. So I go over here, I see 3. n+1 rule, I expect a quartet for these 4 protons. That's exactly what I see. So splitting looks good. And then position, we could say that because it's next to a carbonyl, we have some downfield shift. It's a allylic-like proton. Proton on a carbon next to a pi bond. And this is a pi bond to an oxygen, so there's some withdrawing effects of the oxygen that de-shields these 4 protons and moves them downfield. So we expect in that 1.5 to 2.5 range this signal. So this makes sense, and having the methyl groups in the 0.5 to 1.5 range that are on the ends also makes sense. So this is not it's certain to be the structure that matches this spectra, but the spectra does not invalidate this structure. This structure fits the data. Let's just do this 3 times and we'll be done with this recording. So we just do the same thing. I have 3 examples we're going to look at. So we can take C5H11Br. Now this is different because we have a bromine or a halogen. How do we use the 2n plus rule, or the 2n plus 2 rule minus actual number of H's? How do we use that if we have halogens? Well, we count them as a hydrogen because bromines, think about it, are on the end. They only have 1 bond, so if I wanted to put a bromine into any structure, I'd have to take a hydrogen off to put the bromine in. You've seen that in radical halogenation of alkanes. You had to take an H off to put a Br in. So in our accounting, we just count it as a hydrogen. So we would have, for this case, 12, 2 times 5 plus 2, 12, minus 11 plus 1, since we count the bromine as, in a sense, like a hydrogen. So of course, that's going to give us 0. We have a fully saturated structure, so there can be no pi bonds or rings. So integration, let's look at that. That was our second thing. So we looked at unsaturation. It is fully saturated. Integration, 7 and 1.6. Now you certainly can't have half a proton. So what do we do with these numbers? What you'll do is you'll need to take the lowest signal or smallest signal and integrate it to 1. So 1.6 divided by 1.6 and 7.7 divided by 1.6. So of course this would be 1 if we take 1.6 divided by 1.6. But we're going to take this and divide it by 1.6. That would give us 4.375. Now we know 1 and 4.375 ain't going to work because you can't have a fraction of a proton. And second, we know that we have to get to 11. So we can double that. We can say 1 going to 2 and 8.75. So I've done that in the baseline here. And that's getting us a lot closer. 2 and 8.75 isn't perfect, but if I add these two together, I get 10.75. I'm really close to 11, so I'm going to write this in pen. I have 8.75, no. I have 9 protons. That's close to 9, close enough. 9 plus 2 is 11. I have 9 protons that are equivalent. That's a nice singlet. and I have a nice singlet here, I have 2 protons that are equivalent here. So I can propose to get 9 H's that are equivalent. I can propose 3 methyl groups. And I'm probably going to put them on the same carbon to make them equivalent. So I'm starting to pull together maybe a piece, a fragment. I'm going to propose that I have 3 methyl groups off of a common carbon that's in the structure. This is just again, on the palette, we'd say that's a piece. And I have a CH2 group because I had 2 H's that were equivalent. A CH2 group. So let's put that on the palette. So I can say I have these 2. Now if I look at this carbon here, cannot be this carbon here because we had to have 3 methyl groups off of it. So this carbon can't be seen in the spectra, cannot have a proton off of it. But to make these 3 methyl groups equivalent, the easiest way to do that is to put them all on the same carbon to make 9 equivalent protons. So let's take this piece, combine it with this piece, and we have to get that bromine in. We have 4 carbons here, that'd be 5 carbons, so we're done, and a bromine. Well, the best way to do that is to put then the tert-butyl group on the end. Of course, we can't put the bromine right here because that would not allow us to put the CH2 group in. So let's put the CH2 group in here and have the bromine here. So we're again using pieces that we've made through integration, and we haven't even considered splitting at all. We just proposed this structure. Now we can kind of work backwards, structure to spectra. Let's look at this structure. Would it fit the splitting? Would these 9 protons show a singlet? I think so. Take a representative, any one of these 9. So I pick one of these 3 and take a walk. I go to this carbon. Of course, he has no protons. We've set it up that way because we couldn't have another signal down here. We already had the 2 signals accounted for, 1 and 2. So there is no proton here. We have a singlet for all 9 protons that are in this tert-butyl group. Now the CH2 group, same thing. Take a walk, take any one of these 2. Of course, there's no splitting from the left. We go to the right here. There are no protons off this carbon, so there's no splitting for these 2 protons. We have a nice singlet. And now let's look at position. This is downfield. This one's downfield. Why would that, I guess, still fit the spectra? Well, because the bromine would pull, and it'd be in that, I guess, 2.5 to 4.5 range that we'd expect these 2 protons to fall because they're next to a heteroatom. We'd expect these to be alkyl, somewhere between 0.5 and 1.5, and sure enough, they are. Maybe just a little bit above 1 because of this halogen and its withdrawing effect. So that's kind of the game you play. Our position matched up, our splitting matched up. This structure just fits. Now I'm going to do one more, and for sake of time, kind of leave out the 3rd example. But this is the game you can play with spectra and maybe some information about the molecular formula going to structure. Let's do one more. This one's a maybe fairly simple one. There's not a lot of combinations you can have with 2 carbons, 4 hydrogens, and a chlorine, and 2 chlorines, sorry. Let's look at our degree of unsaturation. We know 2n plus 2 minus actual number of hydrogens divided by 2, where chlorine is just counted as hydrogens. So we really have here 2 times 2 plus 2 would be 6. And that's minus, because 2 times 2, there's the number of carbons, is 2, is 6. Minus actual number of hydrogens, well, we have 4, but we add in the chlorines, that's total of 6, 4 plus 2. And we divide that by 2, of course that's just 0. So we have no pi bonds or rings within this structure. It's fully saturated. Looking at integration, we can do the same thing we did on the last slide. We can divide this by 1.69 to get to a whole number. Divide this by 1.69 to get to a whole number. And so we can say that's about 3.01. So we can start dealing with some whole numbers, and 1 and 3.01 does come up to close to 4. So we can now say what that means is I have 1 hydrogen here and 3 hydrogens here. That's again just a deduction from the integration values. We have to come up to 4 protons. So we can now say in pencil, hey, the best way to make 3 protons equivalent, and it looks like that's either a doublet, and we can resolve that. Here we go into we blow that up a little bit. That looks like a doublet. We're not sure. That looks pretty close to a doublet. Here, this looks like a quartet. You can put it in pencil or question mark. So to make 3 equivalent, we can say again we have CH3 group. We're going to put on a palette then that this is our proposed fragment in pencil and pen, proposing this. And we can propose that we just have a CH group, that has 3 other things bonded to it. That is represented here. We have just a single hydrogen off of a carbon because we only have 1 hydrogen here. Now let's put that together with the 2 chlorines. This is like on our palette. We can pull these together and say, okay, well, the only way I can build this thing is to have this carbon in the center, the 2 chlorines off of it, the H on one side and the methyl group on the other. Maybe. Again, you're putting it in pencil and you're going to go ahead and check it. So we look at the splitting. We'd expect for this proton, we'd expect a splitting of a quartet because we have 3 neighbors. The splitting would be a quartet. It seems to fit. We have a quartet for this proton, and for these 3, we'd expect a doublet. Doublet because you take any one of the 3 again, take a walk. Over here you only have 1 proton. So n plus 1 being hydrogen being the 1, 1 plus 1 is 2. We'd expect a doublet for these 3 protons, and we see that. So the integration and splitting seems to indicate this structure. Let's look at position. This proton here is off of a carbon that's bonded not just to 1 halogen, but to 2. So typically we put this in a 2.5 to 4.5 range, but if you have 2 chlorines off of that, it's certainly possible that we could shift even further from this area to something downfield, because we have not just 1 but 2 chlorines that can withdraw electron density from this carbon and thus this proton and de-shield it. So this certainly makes sense given that we have 2 chlorines. It's really important to point out with this slide, that's why we don't start off with position, because something can be out of position because there's just some doubling of either 2 different one effect or combination of 2 different effects that cause it to be further downfield than what you might expect given some tables or whatever. So position is usually the last thing you consider going from spectra to structure. Then our last one, this methyl group. Again, we have the protons on a carbon that's sp3 bonded to an sp3 carbon. We'd expect 1.5 to 1.5, but it's a little bit further downfield because it's on a carbon that's sp3 that's bonded to carbons that are sp3 that have 2 chlorines off of it. So there can still be some effect of those chlorines on the position of the signal for these 3 protons. So this is the only structure that really makes any sense. We could try others, but I think you'll find you can't just come up with anything better that fits the data. Alright, well that's it. I don't want to have this video be too long. That's the game we can play in going from spectra to structure.